Okay, let's dive into this. Welcome to today's Explainer, where we're exploring the mechanics and stability of spin-stabilized spacecraft. The core principles driving this kind of stability are actually incredibly elegant and intuitive, and they solve one of the absolute biggest challenges of deep space exploration. We're going to look at exactly how engineers have historically managed to keep these multi-million-dollar probes perfectly oriented out there in the vast, complete emptiness of the cosmos.
So think about this for a second. How exactly does a spacecraft stay upright when there's absolutely no gravity? Space is an incredibly harsh, dynamic, and tumbling environment. There's literally no physical up or down out there to anchor to. And yet, a spacecraft is constantly getting nudged by tiny external forces, whether that's solar radiation pressure, micrometeorite impacts, or just subtle gravitational tugs from distant bodies. Without a clever way to maintain its orientation, a probe would just tumble helplessly through the void. It'd be completely unable to reliably communicate with Earth or navigate its trajectory. So how do we keep it pointed exactly where we need it to go?
Well, the answer often lies in what we call a spinner spacecraft. And the foundational concept here is something called the maximum moment of inertia, or MOI. That's the specific axis running right through the spacecraft where it has the absolute greatest resistance to rotational acceleration. To visualize this, just imagine the distribution of mass within the vehicle. Engineers meticulously design these spacecraft to be completely 100% symmetrical around the central axis, often pushing the heavier components farther out from the center. This careful mass distribution guarantees that when the craft is in motion, its natural preference is to just rotate smoothly and stably around that one specific, predictable axis. Once they're up in space, these highly symmetrical spacecraft are spun up to a constant speed, typically somewhere between 10 and 100 revolutions per minute. Now, what's really interesting about this slide is that this continuous motion actively creates gyroscopic stability. In the frictionless vacuum of space, once you initiate that spin, the spacecraft just naturally wants to maintain it. It inherently locks in its orientation without needing continuous, active control from chemical thrusters or heavy internal reaction wheels. By relying on pure physics, the spacecraft effectively becomes its own stabilizing anchor in an otherwise anchorless environment.
Think of the classic spinning top analogy. We've all played with one, right? A stationary top just sitting on a table falls over effortlessly. But when you spin it quickly, it stands perfectly upright, actively resisting gravity's pull to topple it over. A rotating body in space follows the exact same physical law. It's most stable when it spins about its principal axis with the largest moment of inertia. So just like that playground toy, a spinning spacecraft naturally resists physical disturbances and keeps pointing in the exact same direction. The only real difference is that out in space, there's no table and absolutely no air friction to eventually slow that spin down.
And this brings us to a brilliantly simple mathematical recipe for stability, H equals I times omega. In this equation, H stands for angular momentum, which is the ultimate stabilizing force we're trying to maximize here. I is our moment of inertia, which relies entirely on that symmetrical mass distribution we just talked about. And the omega symbol, that represents the spin rate of the craft. Understanding this relationship is absolutely crucial because it dictates exactly how engineers need to build and operate the spacecraft to ensure it survives its mission.
Let's see how this builds into a really straightforward blueprint for stability. It's essentially a three-step balancing act. Step 1. You utilize a larger moment of inertia by designing the spacecraft with its mass pushed further away from its central axis. Step 2. You utilize a faster spin rate. Because these two variables multiply together, increasing either one leads directly to step 3, which is the natural mathematical result of far greater angular momentum. In the vacuum of space, a massive amount of angular momentum essentially creates a stiff rigidity in the spacecraft's orientation. It makes it highly resistant to any of those external disturbance torques that would otherwise knock it totally off course.
Let's move on and see how this builds out in practical design, because this approach offers some massive advantages. We're talking extremely simple attitude control, incredibly high reliability, super low power consumption, and very few moving parts. Having fewer physical parts that can break is absolutely essential when you're millions of miles from a repair crew. But, it also introduces some pretty significant drawbacks. Because the entire craft is spinning continuously, its antennas and cameras rotate right along with it, which means pointing scientific instruments is incredibly difficult. If you want to take a crisp, long-exposure photograph of a distant planet, actually, scratch that. A spinner spacecraft is absolutely unsuitable for high-resolution imaging or precise Earth observations. However, despite those limitations with photography, this elegant, passive, low-tech solution was vital for exploring the deep solar system. Let's look at a legendary real-world case study, the Pioneer 10 spacecraft. Launched way back in the early 1970s, it required an incredibly robust and reliable way to stay stable during a perilous decades-long journey. Engineers back then obviously didn't have the luxury of modern lightweight computing systems to constantly monitor and adjust the craft's orientation. They needed physics to do the heavy lifting, ensuring the craft would survive long enough to reach the outer planets.
For Pioneer 10, engineers utilized a remarkably slow spin rate of just about 5 revolutions per minute. The entire spacecraft rotated at a completely relaxed pace. It didn't need to spin like a blender. Just a steady, leisurely 5 RPM rotation generated all the necessary angular momentum for deep space survival. It's kind of mind-blowing to consider that a spacecraft traveling tens of thousands of miles per hour through the void relied on such a gentle, almost imperceptible rotation just to keep itself safely on target.
So the crucial point is that this simple, slow motion produced a powerful gyroscopic effect that flawlessly maintained the spacecraft's stability over decades. And most importantly, this steady orientation kept its high-gain antenna reliably pointed toward Earth at all times. In deep space exploration, communication is literally your lifeline. Without this brilliant application of basic physics, Pioneer 10 could never have beamed its revolutionary data back from Jupiter and beyond, and the whole mission would have been a silent failure. But Pioneer certainly wasn't alone in utilizing this technique. Looking a bit closer to Earth, many early communication satellites, most notably the Intelsat 4 series, relied heavily on spin stabilization too. These massive communication relays were sent into orbit in the early days of the space age, a time when minimizing weight and complexity was just paramount. Engineers heavily favored this design because it required incredibly little active attitude control hardware, which maximized the satellite's lifespan and reliability for early global communications networks. To wrap things up, spinner spacecraft are fundamentally stabilized by rotating about their principal axis with the maximum moment of inertia. The resulting angular momentum acts exactly like a gyroscope, locking in a highly stable orientation and minimizing the need for complex active attitude control systems. And this brilliantly illustrates how a reliable engineering choice, rooted deeply in the basic physics of momentum, solves highly complex operational challenges in orbit. It is a true testament to doing way more with less, in one of the most unforgiving environments imaginable.
Which leaves us with this final thought to ponder as we close out today's explainer. What other highly complex problems in space exploration can be solved with elegantly simple physics? You know, when we look at the monumental challenges of exploring the cosmos, sometimes the most profound solutions aren't found in a massive supercomputer, but in the timeless, perfectly balanced spin of a toy top. Thanks so much for joining me for this explainer. I'll catch you next time.